Hello students. In the last lecture, we proved the point that half-life of a first order reaction is independent of concentration of reactant. And we discussed this fact that a first order reaction never goes completion. Why this happened, I will explain. And this is the formula which is used for the numerical purpose. This lecture cover numerical problems related to the topic order of reaction. These problems are taken from the previous year questions. So now let's move forward. Before discussing the problem, let's discuss some more booster point. As we already discussed in the zero order reaction, if the initial concentration is not given, what formula is need to be used? So suppose at time T1, concentration of reactant is given as A1, and at any other time T2, the concentration of reactant is taken as A2. Then the rate equation, equation for rate constant can be written as in last lecture, I already told how you can derive that expression for the zero order reaction. In a similar way, we can derive this expression for the first order reaction. Like we know that for a first order reaction, here we need to change the limits only from A1 to A2, T1 to T2. After integrating, you will get this expression. If the initial concentration is not known, you can use this formula for calculating the rate constant or whatever the requirement of questions are. In a similar way, there's one more formula. It is equal to A naught 1 by 2 to the power Q, where Q is equal to number of half-lives, which can be calculated as given time divided by half-life time. That is T upon T half. In some problems in which half-life is given to you and it is asked that calculate the concentration of reactant after 3 half-life time, 4 half-life time, or some other time is given to you, then you can directly use this formula. It is equal to A naught 1 by 2 to the power Q. So these are the boosters which we can use during the problems, although not much problems is asked from this topic, but they can be asked in future. So we need to prepare for each and everything. That's why I'm taking these shortcut formulas to you. Now there's another topic known as average life, the concept of average life. No derivation or nothing is asked from this topic, but it's an important concept. Question can be asked from this topic. So basically, average life is represented by tau, and it is the reciprocal of rate constant K. As we know that for a first order reaction, rate constant K is given as 0.693 upon T half. So we can say that tau will be 1 upon 0.693 is equal to 1.44. So we can say that tau is equal to 1.44 into T half. The average life is just 1.44 times of half-life for a first order reaction. Now, in actual meaning, how we can define this? We know that for a first order reaction, concentration of reactant decrease exponentially. So if we consider T as tau, then AT is equal to A naught minus K tau. And as we know that tau is just a reciprocal of K, we can write e to the power minus 1. So that is at average life, AT will remain A naught upon E. If we calculate this value, we find that AT will be equal to 0.3678 A naught. And we know that AT is given as A naught minus X, where X is the concentration of product. If we find the value of X, we'll get 0.632 A naught. So we can also define average life as the time required in which the concentration of reactant remain 36.7%. You can see that 36.78% reactant will remain after average life, usually used for the radioactive decay, or the time required in which 63.2% reactant get converted into product. You can say the product obtained is 63.2% of initial concentration. So this is the concept of average life. This is the important formula which can be used during the solution of problem which are asked in different exam. Now let's discuss some question which are already asked in the previous year exams. The important question, as I need to prove one point which is written here: if first order reaction never goes completion. See, this is the maximum percentage of first order reaction which can be achieved. So for first order reaction, we can say that T is equal to 2.303 by K log A naught upon AT. First of all, during the answer writing, we need to mention each and every term used in this formula for getting good marks. Here we consider K as first order rate constant, A naught is the initial concentration of reactant, it is the concentration of reactant remain after time T. Now, as we already know that T half for a first order reaction is equal to ln2 by K. For the value of ln2 will be 0.693 by K. We know that. Now, suppose the value of A initial is taken as 100. Then if the reaction complete 99%, then the concentration of AT will remain A0 minus 99% of A. So as we assume A0 as 100, you can write 0.01 is the amount of concentration remain after 99.9% completion. Now, from the formula which is given in equation 1, if we put this value, so the T 99.9%, come to be log 10 to the power 4. In log, power can be taken outside and the value of log 10 will be. Now, take the ratio as we know that calculator is allowed in the exam. After dividing, you will get this value is approximately equal to 10. Which suggests that the time required for a reaction for 99.99% completion is approximately 10 times of half-life. As well as in this equation, if reaction get completed for 100% completion, means the value of AT will be 0. So the ratio of A0 by AT become log infinite, which cannot be defined. So first order reaction will never goes for completion, as we know the exponential decay graph between AT and T suggests that this will not touch with the y-axis. Extremely sorry, beg your pardon. On x-axis. So we can say that the first order reaction never goes completion. It's the similar type of problem which can be asked. As we already know, the 50% is ln2 by k or 0.693 by k. Now I'm taking this problem in a single step. The action is 75% complete. Means if you assume A0 as 100, or don't need to assume, the AT will be 0.25 A0. you will find as log 4. Log 4 can be written as 2 log 2. And we know that the value of 2.303 into log 2 is 0.693. So we can write 0.693 into 2 by k, which suggests the time required for the 75% completion of a first order reaction is twice as that of half lifetime. Now see some more problems related to this topic. Before this is the problem number 3. The previous year question asked in UPSC. For such kind of reactions or questions, better to write the initial assumptions. Here we can write A naught is taken as initial concentration, AT is the time required, AT is the time, AT is the concentration of reactant remain after time T, X is the amount of product formed. These are the assumptions. Whatever the assumptions you are using, you must need to mention in the problem. Now, as we know that if the reaction follow first order kinetics, the value of rate constant must be same for the each step. This is the equation used for the calculation of rate constant of a first order reaction. Now, from experiment 1. One more thing is given to you, that at time 0, the concentration of A is 50.8. We suggest from the data, the value of A naught will be 50.8. Now from experiment 1, that is after 900 minutes. The concentration of AT remain will be 19.7. So we can calculate, put the value of T here. Value of A naught is 50.8. We can use calculator during the exams. So I'm directly taking this value as 0.001, which come after the calculation, which suggests that the value of rate constant, not second inverse, time is given in minute. Now say from experiment 2 or second observation, that is at time T is taken as 1800 minutes. Similarly, here AT is given to you. The value of AT is 7.62. .8 is the value of A naught. The value of AT will be 7.62. Also come. So this data suggests that the equation is first order, as each and at every moment or at every time given in the question give the same value of rate constant, which suggests the reaction follow first order kinetics. Now there's a one more case. First order gas phase reaction. If the reactants are in gaseous phase, here P naught is the initial pressure of gas A taken in the container. After some time, the pressure of A is given as PT, and we know that after some time we get a mixture of gas, and in the mixture of gas it is very difficult to calculate the individual pressure. So it is easy to calculate the total pressure of gases mixture in the container. So P total is the total pressure. So this is the expression which we can use directly during the numericals. For the calculation of time, where n is the number of products. Suppose A equation is given to you that A gives P after decomposition. In this reaction, only one product is obtained. So if we put the value of n here, we will get the expression of first order reaction as A gives B plus C. We will get two product here. This is the formula you can use directly for calculation of time or rate constant for a first order reaction in gaseous phase. These are the some other problems. Here you didn't know how to prove this, but I think proof is not required here. But this type of problems may be asked during the exam. So we need to understand how we can find a relation between initial pressure, total pressure, and the rate constant if the reaction taking place in gas phase. Suppose initial pressure of gas is P naught. Here the pressure of reactant remain after time t. As I told you earlier, we cannot calculate the individual pressure easily, but we can calculate the total pressure after time t. So if you see, the total pressure of gas will be the sum of all these pressures. So from here we find that P total will be equal to P naught plus 2x. That is, x will be P total minus P naught upon 2. Now, if you need to find the value of pressure at any time t, put the value of x here. You will find that the value of Pt is 3P naught minus P total by 2. In the general expression, we can replace A naught to P naught and AT to PT. We can write that for a first order reaction, T will be given as 2.303 K log P naught upon PT. So in place of PT, if we put the value, we find that the expression is the relation between the rate constant, initial pressure, and the total pressure of gas in a first order reaction. We take some more examples. See, here it is asked that decomposition of nitrous oxide. This is the problem which you need to solve your own for the practice. Let us take one more example for understanding the topic well. In question, it is given to you that a reaction takes 40 minutes for 25% completion. Means T 25% is given to you as 40 minutes. So if we assume the concentration as A naught, after 40 minutes, it will remain 0.75 of A naught as 25% get completed. Then 75% will remain. Now the time required for 75% completion is asked in this equation. As we know that for each percentage of reactant, the rate constant will remain same. So if the reaction completes 75%, which means 0.25 of A naught will remain after time t. So if we divide the 75% to t 25%, what you get? This will comes to be log 4, and this will be log 4 by 3. Log 4 can be written as 2 log 2, and log 4 by 3 can be written as log 4 minus log 3. If you put the values of log, you will find the relation. This is the problem which is asked in previous year section, but it's a quite similar type of problem which we discussed already. Here we are taking the decomposition of N2O5. And the volume of oxygen is taken as an experiment value for the measurement of rate. And the value of volume is given at different time t. So you need to prove that the reaction follow the first order kinetics. So we know that the formula of time rather than time, we need to take as the formula for the calculation of rate constant is given as. But in this equation, the value of volume of oxygen, which is one of the product in this reaction, is given to you. We know that AT is A naught minus X. I think there is something missing in the problem. Yes, infinite time is also given in this equation. So we need to consider time required for the completion. See, T infinite means reaction goes to completion, and you know that reaction get complete when all A naught get converted into O2. So it is the initial amount of N2O5 which is given to you. So A naught will be 84.6. Now consider experiment 1. When time is 40, AT will be equal to A naught minus X. A naught is 84.6 and X is given to you as 15.6. It will becomes to 69. From here, you will get the value of K. After calculating, you will get approximate the value of K as 5 into 10 to the power minus 3. Similarly, if you take in the experiment 2, you'll find that after 80 minutes, AT can be calculated as 84.6 minus 27.6 is equal to 57. Again, apply the formula. Let me calculate this. Getting this value as approximately 4.94 to 10 to the power minus 3, which is approximately equal to K. So these two steps suggest the value of K remains constant. Thus, reaction follow the first order kinetics. So in this video, we discuss the problems which are asked in the previous year sections related to the topic zero order and first order reaction. In future lectures or in next lecture, I will discuss nth order reaction, how we need to proceed, second order kinetics, third order kinetics, or more than that. However, most of the questions are asked from first order and second order. So we need to focus on first and second order. But as a precautionary measurement, we need to understand the nth order. So we will discuss that in the next lecture. Till then, do practice for such kind of questions and send me the doubt